Hello, everyone. Welcome to this series of lectures on inorganic chemistry. We've already seen variation in atomic and ionic radii across period 3. The next physical quantity that we're going to talk about is the variation in melting point. Okay, variation melting point across period 3. Okay. We go to talking about the variation in melting point, we need to ask ourselves, what does melting point depend on? Melting is breaking the solid and converting it into a liquid. So it's an endothermic process. It involves absorption of energy to break either bonds or intermolecular forces. Whatever is holding the solid together needs to be broken. Okay. And depending on the structure and bonding of the different elements found in different elements, you'll find that you will have to break different types of forces. Okay, so melting point depends on the structure and bonding of the elements in the solid state. Okay, and if we look at the elements across period 3, you'll find sodium, magnesium, and aluminum are metals. Yeah, sodium, magnesium, aluminum, they're metals. Right? They're metals. And they have metallic bonding. Okay? They show metallic bonding. Silicon is covalent, it's non-metal, but it's got a structure similar to diamond. So it's a covalently bonded macromolecule, similar to diamond. Chlorine, going from phosphorus through sulfur. Okay, phosphorus, sulfur, chlorine, and argon, though technically I wouldn't call it a molecule. All of these are simple covalent molecules. Yeah, they are simple covalent molecules. Right? So the structure itself is different. The bonding that's found in the different elements is different. Okay, but one more thing that we need to remember is that though we write phosphorus as Sp, phosphorus in nature occurs as the P4 molecule. It's tetraatomic. Sulfur is octaatomic, 8 atoms. Chlorine is diatomic, it is Cl2. Argon is monoatomic, hence the hesitancy to call it a molecule, since it's just an atom. But so what are the forces that are holding these structures together? In metals, the forces holding it would be the electrostatic force of attraction between the cation lattice, the delocalized free electron C. Okay. Basic grade 9 metallic bonding, you talk about the ions being arranged in neat rows and columns, called as your lattice, and surrounded by a sea of delocalized electrons. While in a macromolecule like silicon, which is similar to diamond, you only have strong covalent bonds, okay, holding the atoms together. While in simple molecules like phosphorus, sulfur, chlorine, argon, you have instantaneous dipole to induced dipole interactions. ID interactions called as your London forces or your van der Waals forces. All right. So of the three types of forces, you find that the covalent bonds found in silicon, okay, macromolecule are the strongest and need the highest amount of energy to break. And hence, silicon has the highest melting point in period 3. Silicon has the highest melting point in period 3 because the covalent bonds holding the macromolecular structure are very strong and need the largest amount of energy to break. The next strongest in that list happens to be metals. So basically, metals will have higher melting point because metallic bonds are stronger than ID-ID interactions. So metal have higher melting points. But among metals, the melting point is of the order. You basically would have aluminum with the highest, followed by magnesium, followed by sodium. All right. This is because the charge on the metal cation, decreases as we go across the period. The sodium forms a +1 ion. All right. The magnesium forms a +2 ion. Aluminum forms a +3 ion. So as we go across the period, the charge on the metal cation increases as we go across the period. As we go across the period. So the attraction between the metal cation lattice and the delocalized sea of free electrons increases as we go across period for metals. So the melting point would be that aluminum would have the highest, followed by magnesium, followed by sodium. Now coming to the ID-ID interactions. All right. Phosphorus. Phosphorus, sulfur, chlorine, and argon are simple molecules which have instantaneous dipole to induced dipole interactions. Interactions. The strength of the ID-ID interactions we've all studied depends on the number of electrons present in the molecule. So we're just looking at the element. That will be phosphorus with 15, sulfur with 16, chlorine 17, argon 18. But it's the total number of electrons in the molecule. So if you look at it, P4 would have basically 4 times 15. That is 60 electrons. Right? 60 electrons. S8 would be 8 times 16. That is 128 electrons. Chlorine 2 would be 2 times 17. That is equal to 34 electrons. While argon basically is just 18 electrons. 18 electrons. So among them, sulfur has the highest number of electrons, which means sulfur has got the strongest ID-ID interactions, and hence would have the highest melting point. So melting point is of the order. Is of the order. You basically have argon with the least, right? Argon with the least, followed by chlorine, followed by phosphorus, followed by sulfur. So the overall order. So the overall order of melting point in period 3 is as follows. The least would be argon, followed by chlorine, followed by phosphorus, followed by sulfur, and next comes sodium, magnesium, aluminium, and finally silicon with its macromolecule. Okay, and we can put that as usual in a graph. So, okay, let's say I plot melting point against identity of the elements, say sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, what we're doing is not a very exact graph, it's more of a trend line. Okay, nothing more than that. So the trend is that from sodium to aluminium, it increases. Okay, just looking at the trend, not looking at data. From aluminium to silicon, there's actually quite a bit of a spike. Okay, from that to that is quite a bit of a spike. Then you come down from there to phosphorus. Okay, come down from there to phosphorus. Remember, phosphorus is way lower than the sodium. So let's keep that in mind as well. From phosphorus to sulfur, there's a slight, ever so slight increase. And then goes down pretty bad to chlorine, which is a gas at room temperature. And even more for argon. So this is the trend that we get. Okay, I hope that was clear. Okay. So I'll be posting more on this, and hopefully this is of use to everyone. See you later. Bye-bye.